I'm Sarah, and I'm a technical director at the Financial Times. I've been at the Financial Times for 10 years. We are one of the world's leading business and financial news organizations. And we started moving to the cloud not long after I joined. And initially that was through developing a private cloud, and then we moved to AWS. I would say we've had a pretty cloud native approach for the last 5 years, and I'm going to talk about the things that we learnt while moving to that and since we've been doing that. But I want to start by saying about what I think cloud native is. And I think often people think about the cloud native computing foundation and they think, oh yeah, it's Kubernetes, it's service mesh. But I think it's broader than that. It's really about building systems that benefit from the cloud rather than just running on it. So, of course, you benefit from just moving your systems to the cloud, doing a lift and shift where you take your monolithic application in your database server and you run them in the cloud. You get benefit from that. You have someone else doing the infrastructure work. So a lot of work that you used to have to do in your organization is now done by the cloud provider. You aren't racking servers, and if something fails, you can spin up a new machine. And you can even make that happen automatically through auto-scaling. And you also have much quicker provisioning. So it's a lot quicker than when someone had to buy a server and put it in a data center. And you can create a new server with the click of a button. And this shows how long it took at the FT to get a new server ready for code to be deployed to it. So in 2011, these were our own servers in a data center, and it took a long time. You had to order in a server and rack it up in the data center and configure it manually. Everything was manual. In 2012, we started developing our own private cloud. By 2014, we started using AWS alongside that, and it took minutes to provision a new server. You also get easy scaling. So scale up or down very easily to meet demand by having more instances, or you can change to a new instance type. And this is a change from the time before where we used to have to think about our capacity planning. So there's a lot more flexibility to say, let's spin up this new product, see how it goes. We can choose whether we think it's successful. We don't have to predict how many people are going to use it 6 months to a year in advance. And of course, you can more accurately assign costs to a particular application because you're paying for the EC2 instance, you're paying for the lambdas. You're not having to work out the overhead of data center costs. So even the minimum move to the cloud has a lot of benefits, but I think you can get much more benefit if you're willing to change the way you build and operate software. And obviously that's quite a big if. It's basically becoming cloud native involves quite a big change. The first thing is continuous delivery. So you need to have continuous delivery. It's about automating your deployment pipelines that should incorporate automated testing, and it lets you release small changes frequently. Once you have that, you can adopt some kind of decoupled architecture. So that could be microservices, where you're breaking a monolith down into small services with clear defined boundaries. Or it could be something else like AWS Lambda, something that's decoupled that lets you make changes in one place and be relatively comfortable that you're not impacting somewhere else because the architecture keeps things separate, gives you a small blast radius. This is perfect. I have just had an alert saying that my company wants to upgrade my Mac. Right, I've just turned that off. Right, so it could be Lambda. Once you adopt microservices, adopting containers and orchestrations is an obvious next step because you want to package up all of your processes and libraries for a single application, put an interface on it so you can move it around as a single thing. And then you have the ability for orchestrators to use this to, among other things, dynamically manage your system. So if a server fails in your cluster, you can have all the instances spun up on other servers in that cluster. Another advantage of containers compared to VMs is that they start up much more quickly and they take up less space. So you can pack a lot more containerized applications onto a single large VM. And we saw about a 40% reduction in costs, moving from one microservice per VM to a containers and orchestration approach. And each new service you build takes a little less effort. You're not spinning up a VM for it. You're just defining the characteristics of how that service should be deployed. And finally, you can take advantage of X as a service, something else that you can hand off to someone else, whether it is using databases provided by your cloud provider, whether you move to a managed platform. So often with the first stage of moving to the cloud, people install software onto a VM, and that's what we did at the FT. We had, I worked on the content platform platform. We had a MongoDB cluster that we managed, and we even containerized that cluster. But that's not key to the business functionality my team were working on. So later, for a slightly different use case, we didn't install a database. We used AWS Aurora because it's a lot quicker to get going on that. And I think people worry about vendor lock-in, but vendor lock-in is probably less of a concern than moving slowly because you have chosen to take an approach where you're trying to do everything yourself. You want to hand off this operational stuff. Another aspect to this is if I wanted to try out a new database before we moved to the cloud, I had to go through a procurement process. I had to form an agreement with that company. With the cloud, I can try something out. So I can try out a graph database. If I'm on AWS, I can just say, right, they offer this type of data store. Let's try it. So you move more quickly. Many teams at the FT use a PaaS. We deploy a lot of applications onto Heroku. That's what's used for our ft.com system. So I haven't really explained why I think all of these things together pay off. And the answer is because if you do them right, you get to deliver value to your customers more quickly. So things change when you can get from an idea to production in days rather than months. It means you can experiment because you haven't invested a lot of time or money in an idea. So sunk cost makes it really tough for people to say that didn't work, let's abandon it. But if you haven't spent a lot of time on it, maybe you will do that. And an example here is an idea we had at the FT about how we represented our film reviews. So we decided we wanted more people to read film reviews. And we added the rating that the reviewers had given onto the page that listed all our film reviews, thinking this is going to increase engagement. And what it actually did was it meant no one actually clicked through to read the review. They just saw the score. So we removed it because it didn't take us very long to do. And these small releases lower the risk for each release. It's easier to work out why something isn't working and to recover from the change, either by rolling back the release or by fixing it quickly and rolling forward. So Accelerate is a great book. I highly recommend it. It is basically about what it takes to build high-performing software development organizations. And what the authors mean by this is organizations that positively impact their organizational performance, profitability, market share, productivity. And there are 4 key measures that this book identifies. Targeted at outcomes, not outputs. And they are delivery lead time. So how long does it take between you committing the code and it going live? Deployment frequency, which is really a measure of how small your changes are. So it's an inverse relationship. If you're deploying hundreds of times a day, you're probably releasing small changes. When things do go wrong, how long does it take you to restore service? That's generally something that improves as you automate your pipelines because you use the same process to roll forward or to roll back. And change failure rate. Of all the changes that you make, what percentage of them do you have to do something because it went wrong, either to patch it or to roll it back? So the goal is to move quickly with small, low-risk, reversible steps. And if you do this, you have a positive impact on your business. It improves all of these metrics. So an example for us is deployment frequency. So before we moved to the cloud and we had a monolithic application with a relational database, we couldn't do releases out of hours, in hours. We had to do them out of hours because they took a long time. And we had to freeze the website and we couldn't publish the news while that was going on. So we did 12 a year. So it was once a month on a Saturday. That's changed significantly. I ran a query last week. We did about 3,000 releases in the last 4 weeks. It's over 100 a day. It's probably about 30,000 changes a year compared to maybe 50 when I joined the FT. So we release code at least 500 times as often. And the change failure rate is much, much better too. With those 12 a year releases, maybe 1 or 2 failed. So that's 15 to 20%. Now it's under 2%. So it's definitely been worth it for us in terms of ability to get value out quickly. But it does mean changing a lot of things. And I think there are 3 sort of fundamental reasons why things need to change. So to be able to release changes hundreds of times a day, you need to reduce the amount of time you spend waiting. So whether that's waiting for access to a shared resource, like a staging environment for testing, or for a decision, or for a meeting. So it's not just systems that need to be loosely coupled. Your organization needs to be loosely coupled too. And that means that you need your teams to be pretty autonomous and empowered to make their own decisions. And this can be a scary thing to do. You have to explain what the expectations and the responsibilities are for those teams, and it'll probably work out. And then you have to accept that distributed systems are different, they're unreliable. Calls over a network fail. In process calls being replaced with a network call, you're more likely to have problems. So you need to build with resilience and redundancy much further to the front of your mind, so that small periods where parts of your system are unreliable doesn't impact the ability to serve business needs. So with that in mind, what changes? And the answer is, I think lots of things change, which is why going cloud native is not something that happens overnight. It's a culture change. Culture change is hard, it takes time, and you don't always manage to take everyone with you. And you need really to have backing from the top to do this kind of thing successfully. So I'm going to talk about these 6 areas and what I think the key things are that you have to focus on to do it successfully with this change. So I want to start with talking about deployment, because I think getting this right is key. You need to be releasing small changes frequently. And people often automate their deployment pipelines and think, that's it, we're doing continuous delivery. But unless you're using them to continuously integrate code and release it to production, you aren't doing continuous delivery. So the whole point is to avoid cases where developers end up with lots of changes locally that haven't been merged with other people's code. Should be committing code to master every day. It should be going live without having to wait for any long-lived manual process. And that means that you have to change things that perhaps were there in your organization. So no change advisory boards, no change request forms. Often the first response when you start talking about this is for people to worry about auditing. I think by this point we have plenty of examples of how you can build an automated pipeline that's better controlled and audited than what came before. And we have plenty of examples of people in highly regulated industries like banking who have got automated deployment pipelines and do continuous delivery. You can't fill out manual forms if you're doing hundreds of releases a day. We used to have a change request form that we would fill in, and at one point I worked out with the number of releases we were now doing, it would have been 67 days a year just filling out that form. So that doesn't work, but we still see the value in knowing what changed. So we have an API and we wire it into our deployment pipelines. It's much less time to do it. There's no manual work involved, and actually it's much more accurate. Change advisory boards, the idea of a meeting where you say, okay, these are the changes we're going to release this week, which we had at the FT when I joined. They're a reaction to the risk of making a big release all at once. Once you move towards smaller changes with a lower blast radius, the risk of failure for each release is lower. And Research and Accelerate says that a change advisory board actually doesn't reduce the risk of failed releases. It makes no difference one way or the other, they found. It just slows the ability to do releases down. You don't need to choose speed or stability. I think there's this sort of false idea that you move fast and break things, or you go slowly and then you're fine. Actually, moving fast means we break things much less. And when we do break them, we're able to fix them much more quickly. Related to being able to move fast, you can only release on demand if you release without downtime. And in most cases, we do this by having multiple instances of a service and doing a rolling deployment. We tend to be using databases that are schemaless, so we don't have that large amounts of data in a schema transformation that used to be quite painful. But if we do, then we run multiple regions, fail over in one region to upgrade the other. Once you can release without downtime, the nice thing is you generally release during standard working hours. And this is a graph that, again, I looked at recent releases, and I can see that most of our developers are based in the UK and Bulgaria. We have a few in Manila and in the US, but generally people are releasing during their working hours. And a nice side effect of that is that if anything does go wrong, you've got everyone that might be able to help you there and able to help. You don't have to wake people up. You can also, of course, reduce the risk by separating releasing code from releasing functionality. And there are a couple of key things here. Something like a canary release, where you release a new feature to a subset of your customers. It has much less impact if it doesn't work. You can release to 1% of people and look at metrics. So here, this is a graph showing that we released a canary. The response times were around what we would expect. We'd have been looking at the errors as well. And then we basically shut the canary down and release the code to everyone. You can also use feature flags. So you're hiding the new code inside a conditional. It means you can check code in whenever you like, but wait until a low impact time to turn on the feature. So for us, we would avoid times where there are big things happening in the news. And of course, you can turn the feature on just for some people. So we can test in production by having people go and test by turning the flag on for themselves. And both feature flags and canary releases were built into ft.com from the start because they're so useful. So obviously the way you architect a system changes when you adopt microservices and continuous delivery. And I'm not going to go into enormous depth because there's so many things you could talk about here. I just want to touch on a few things that we found really helped us with this approach, or that caught us out. So the architecture of each individual service is different when you move to a distributed system because you can't really rely on other services being there long term or being in the same place long term. When we first started building apps, for microservices, we realized that we tended to expect that an application server would start up and the database would be there and ready to accept requests. We were used to the idea that we start things up in a particular order. It's not a good expectation in a microservices world. So you really want to build applications for resilience so they shut down nicely, so that they retry to connect if they can't the first time, and so that they check with a service registry or DNS to find out where the service is that they need to talk to. Normally they're talking to a load balancer, and the load balancer is balancing requests among the instances that are healthy. And I think the thing is, you should have been doing this sort of resilience anyway, but you can get away with things longer when you have two monoliths, irregular releases, and you do some manual process where you always restart the database server before the application. For resilience, it makes sense to avoid synchronous calls. They couple things together. If you can use a queue, your producer and your consumer are not reliant on each other. If the consumer is down, the producer still writes things onto the queue. And a nice impact of this is it also increases decoupling at build time. So if you've got some new need for this information, we can process this as a new way. Your producer doesn't need to know anything about it, and that's really good. And an example is the simple system at the FT, which is that change API that I mentioned earlier. So this is called when you are releasing code. And it's heavily based around a queue. The previous version of the change API used a synchronous call. So you made a call in and we attempted to update the database, and then we returned and told you whether you're successful, which meant that build pipelines would fail because they'd failed to register the change. So we changed it so we just validate that what you sent us makes sense, and we put that information on a queue and say, yeah, go on, you can do the release. It is the change API's responsibility for dealing with failure to write to the change database. The other nice thing about this is we're just showing here there's a Slack consumer that is basically taking the change information and writing it to Slack, but obviously you could also easily add another consumer and write it somewhere else. So we were able to migrate where we stored information for our changes just through writing one Lambda. Transactions, I can remember when I was dealing with monolithic applications and databases, spending a lot of time worried about transactions. But we often run in multiple regions for our critical systems, and it's quite hard to set up database clusters that work across region boundaries. But even if we manage to do that, actually one of the benefits of a microservice architecture is a polyglot approach. So you probably have multiple types of data store. We do in our content platform. We store complete articles in a document store. We have a graph database where we store the web of content and metadata, and we have a search instance as well. What that means is we have to be comfortable with eventual consistency and partial failures where some store or stores don't get an update. I feel like planning for eventual consistency is sensible anyway. We're lucky because for content publishing and delivery part of the FT that I've generally worked on, the events we're processing is idempotent, so we can opt for a write at least once approach. You're always choosing between write at least once or write at most once. Write exactly once is not a sensible goal for a distributed system, but so for us, we can republish these items of content, and that's absolutely fine. That works very well for us. My colleague Matt recently wrote up how ft.com maintains content in two separate Elasticsearch clusters, one in the US, one in the EU, that do everything completely independently. And if they get out of sync, a health check will flag that the two clusters don't have the same count of content. As well as processing notifications, there's a simple process service that makes requests to the content API for recent content. So basically, we say, well, these are recent articles. Let's go and check whether there are any changes. And that often fixes any inconsistencies. But basically, sometimes things get out of sync. There's a small amount of manual work. It'll probably fix itself due to this processor. And the interesting thing about this is that it's a very simplistic architecture and one that people often propose we should improve on. But it's been working for 6 years. It's been working for 6 years and never been a priority to fix. So maybe that's okay. Another related example of keeping it simple comes from another team at the FT. And this is about the key information about our systems that we use during an incident, what we call the runbooks. It's stored in a graph database along with a lot of other system-related information, and we only have one cluster. But clearly, information we use for an incident needs to be highly resilient. It's the troubleshooting information for critical systems. But rather than try and work out how we can duplicate our cluster with all the synchronization issues that might involve, instead we just extract that key troubleshooting information regularly and store it as files in S3. So our runbooks are highly resilient. It doesn't actually matter that they're not updated regularly because they don't change that often. We can update them every day and we'll have good information. So it's about trying to avoid doing complicated things if there is a slightly simpler approach that you can take. So that's the kind of architectural side of things. And I want to talk about how you build things. So I'm thinking here about the next level down from architecture. What do you need to build into your services or around them? So distributed systems are complex systems. And what that means is that they're generally running in degraded mode. And there's a classic paper by Richard Cook that applies. So, effectively complex systems are in degraded mode. And that means you should accept that things will go wrong, focus on resilience and redundancy. So you have multiple instances of services behind a load balancer. So you're directing traffic only to the healthy instances. And you make sure that you build things in so that a calling service will retry. But those retries probably need an exponential back off because you don't want to hammer a service when it's just getting back onto its feet. So you might try after a second and then after 2 seconds and after 4. But I think what we found then is when things start to go wrong, you can end up with a lot of work that is just pointless. So somewhere near the top of your stack, you probably have a timeout where you abandon work or you don't return a response after, say, 10 seconds. So any work you're doing below that point in your stack after that timeout is wasted work. So it's a good idea to think about passing through that deadline as maybe as a header on a request so that services can check whether they should just not even try and process the request because actually it's too late. That will reduce load on lots of your services in the event that you have some problem with latency. Often if you look at incidents that are reported for highly distributed systems, there's kind of an effect of things go wrong and then they compound because all of the things you've got that are trying to recover from it are basically building up and building up. So try and protect yourself from that. When things do go wrong, you want to be able to work out what happened. So observability is about inferring what is going on in the system from external outputs. And for software systems, these are generally logs and metrics and monitoring. So when you had a monolith, it was possible to jump onto a box and grep for logs. And in the worst case, you'd find it was on the other server and you go and do the same thing again. With microservices, any event you're interested in likely went through multiple services running in different places. And two similar events may take a completely different path in terms of the instances that do the processing. So you need all your logs to be sent to a central place where you can see the whole event. And you need a way to be able to see the whole event by tying those logs together. So structured logs with some unique identifier per event. And what we have at the FT is a library that will look for a particular header that has a unique ID on it. If it doesn't see one, it will mint a unique ID and add it onto all requests it sends out, any log messages, any events that it puts onto a queue. So what you find is people automatically do this because it is so useful in the case of any problems to be able to say what happened as part of this processing. If there are millions of checks happening every day, then a 1 in a million event happens every day too. So you get a lot of transient noise. Some instance had a problem, it got restarted by the orchestrator, but something went red briefly. So you really want to know when something's really wrong, and you really want to know where to focus your attention. Often with services that are all interconnected, you can see a lot of things go red because some fundamental thing went wrong. We're trying to tackle this by adding business-focused monitoring. So we identified some key capabilities for the Financial Times. Can people subscribe? Can a journalist publish to the website? And we're looking at very targeted monitoring or testing that tells us whether that capability is okay. So my ideal would be we have 10 tiles, and if they're all green, I could comfortably say we're in a good state right now. One thing that we definitely have realized after doing this for several years is that upgrades and migrations will cause you a lot of pain unless you think about how you're going to approach it. You're always going to need to migrate something. Maybe you built something from scratch and now there's something you can buy in. You know, we built our own service orchestration, but we moved to Kubernetes when it was ready. Maybe you just need to upgrade versions of a database because it's deprecated, or you bought a tool and you've realized it was a horrible mistake. You want to replace it with something else. Or maybe they've now decided to change the way you charge you and you just can't afford it anymore. So you need to build things so that you can migrate 150 services to something new without a huge amount of work. And that does mean automation. So your deployment pipelines should be templated so that you can add a new step into the deployment without having to do it manually in 150 places. Let's say, for example, your security team says we're now going to scan, do security scanning on every build. You need to work out how to patch your services. We have some tools that will automate creation of PRs against a whole range of services based on the need to upgrade something. Related to this, though, some of your microservices may not change regularly. We have some that you know, honestly, there's been no code checked in for a couple of years. You don't really want to find out that they don't build anymore at the point where you urgently need to patch them. And some teams at the FT actually build their services every night. So you pick up issues with not being able to build the new service. They don't necessarily deploy them, but they build them. So that's some of the things that have helped us with building systems that we can support. I think testing was probably one of the things that took us a while to get to grips with and really changed as a result of doing multiple releases every day. So every service needs automated tests. You want something that's quick to run, that captures regressions and that sits in your deployment pipeline, but also that developers can run while they're writing code. For microservices, I tend to think the best return for automated tests is doing them at the boundary of a service, so making a request in and looking at the responses. So Cindy wrote this fantastic blog post on testing microservices, where she points out that if you're testing A's interaction with B, you don't really want to have to spin up C, D, and a Redis instance. So you are better off to mock out B. Because you don't want to run a test that forces everything to be there. Because when you have acceptance tests running locally, you force your developers towards running a full stack on your laptop. And that is difficult at best, especially where you have a mix of operating systems across the team, which we did. And in some cases, it's impossible. Some cloud providers don't exist locally. And the config connecting the cloud provider services into your business logic is also part of the solution, so it needs to be tested. But really, if you run acceptance tests across your entire stack, you just build a distributed monolith, which is the worst of both worlds. You're still thinking about this as a single system. To some extent, you've coupled it, but now it's a monolith where the communication is over HTTP. And when we started work on the content platform, we did build a suite of acceptance tests for testing the publishing of content. Developers had to run pretty much the entire stack locally to be able to run the acceptance test pre-commit. And I think that is a bit of an anti-pattern. And it's a lot of effort to make sure it keeps working. So what do I advise instead? Well, really testing in production. So it's the only place with the full system complexity, the full data, and real user behavior rather than our best guesses at that. For FT.com, it's the only place to test. We don't have a testing environment. There's the developers' laptops, the automated testing in the build pipeline, and there's live. Other parts of the FT do have staging, but many don't. And people tend to worry about testing in production, but there are lots of ways that you can do this. There's another great blog post from Cindy all about testing in production. So canarying and feature flags, they're part of this. And there are lots of tools that minimize the impact on your customers. You want to test your infrastructure too. I see chaos engineering as a kind of testing. So you're testing that your infrastructure works the way you think it does when things degrade. You're testing that you actually built redundancy and resilience in. And maybe you thought you had, but until you tested it, you don't know. And one example I use for this is many years ago, when we were still in the data center, we wanted to test that we could fail over to run entirely out of one data center. And we scheduled this, talked a lot about it in advance, came in on Saturday to test it, deliberately broke the network connection into one of the data centers and discovered that the tool that was meant to do the failover only worked if both data centers were available. So we've immediately found something really useful, abandoned it, went home, said, right, okay, we're going to do this another time. We have to get this fixed first. So our assumption was completely wrong, and that's what chaos engineering is about. It's not about breaking things. It's about testing that things you expect to have work will do. Another thing that I think has to change with the move to cloud native is how you support your systems. So I think the team that builds the system has to be the team that runs it. So this is adopting a DevOps mindset. The kind of things that go wrong are often sufficiently complex that only the team that works on the system day to day has a chance of working out what's happening. You can't hand things off to another team if they're changing multiple times a day. You just can't bring them up to speed. It just slows you down. And you want high-performing teams to be able to make their own choices of technology. So if you're empowering your teams so that they don't have to wait for external teams to decide on something, they don't have to pick from a very constrained set of architecture, but you can't have a central team supporting that wide variety of technology. But the main reasons that I think that the team that builds a system has to run it is because actually you build things differently when you have to respond at 3 a.m. So, we will build in some monitoring that will automatically fail over if this good to go endpoint is failing. This is good. You're the best people to decide how to monitor your systems. And if you're thinking about running them when you build them, you make different architectural and design decisions, and they will reduce the amount of problems that you have. The final thing I want to talk about that changes is the way you're set up to deliver software. So empowering teams and focusing on speed doesn't mean there aren't central teams with a broader remit. You don't want every team in your organization to have to solve the same problems. So you want to have central expertise in things like cybersecurity or observability. But these central teams need to work in a particular way to be successful. And I'm a big fan of this team topologies book. And it's about how you organize your team so you can move fast. And it describes ways of working that closely match what we've ended up with through trial and error. So the idea in team topologies is you have these stream-aligned teams that are working to develop new product features, but you also have other teams that support those teams. And there are two that I want to talk about. The first is platform teams. These are teams that are building platforms that stream-aligned teams use. So maybe, we have a team called Cloud Enablement that manages how people use the cloud. They are protecting people from mistakes. They're making sure we have granular AWS accounts, that permission and access is locked down. We can focus on costs. They provided tooling that means you can tag non-production instances, so we close them down overnight at weekends. If we close systems down overnight and at weekends, we can save quite a large amount of money. And that's something we can do centrally. That team can know about new instance types. They can know about the new things AWS have released, and they can make sure we make the best use of things like reserved or spot instances. And there's sometimes, I think, a good case for a platform team at the next level up. Kubernetes is quite a complicated thing to run, and a pattern I've seen working elsewhere is there is some team running a Kubernetes platform and providing those stream-aligned teams with tools to use it. The second thing I want to talk about is enabling teams. So these are teams that have expertise in a particular area, and they do things that allow other teams to be more productive. Maybe they build tooling, they provide insight, they offer expert advice and training. So something around cybersecurity, observability, web infrastructure. And those teams need to make things self-service. They need to have great documentation. You don't want to have people having to come for you and wait for you to do something. So it's really about making sure that is as asynchronous as you can do. And there's a lot in the Team Topologies book about how to work across these different types of team effectively. One thing that you can make all of this hang together is to provide some kind of guardrail, some expectations from delivery teams and how to meet those expectations. We're starting to work on this a lot this year. So these are the things that say, well, what do you want to do when you're building an app? What do you need to consider? And the first thing would be, do you need to build it? Could you buy something in? Is this core to our business function? Is it critical to us? Is it a differentiator? Or could we just pay someone else to do it and use our teams to do something that gives us better value? The second thing we want to document more is the technologies that we actually recommend at the FT. We don't want every streamline team to have to go and work out which is the best data store that they could use for a particular reason. So we're starting to develop a golden path at the FT where we'll document, here are our recommended data stores, for example. And if you're going to use them, here's how you should back them up. Here's how you should restore them. Sharing that expertise that we're gradually developing in different teams. So Golden Path will be about having a default that lets most people just get on with delivering business value. So in summary, it's a transformation going truly cloud native. It affects a lot of the way that you do your job, and it takes time. And it's a multi-year thing, really. You get value earlier, but it is going to take an investment to get there. I think it is worth doing because it transforms your ability to deliver value to the business, because you can do small, low-risk changes that go live all the time. And I think you can build a software development organization that delivers higher value to the business, but also is more interesting and enjoyable for the people inside that software organization to work, because they're not waiting for someone else to make a decision. They can be empowered and say, this is the best way that we should approach that. So thank you. If you're interested in knowing more about the way the FT works, we have a product technology blog that covers architecture, process, lots of things like that.